So, a couple things off the top before we get going, some housekeeping stuff. We're diving into material. Two most, I think, common problem kind of seeing with Stata if you're still having issues kind of opening files and getting that on your computer. On Tuesday, I mentioned it. I don't think I did on Thursday, but you have to make sure that your cloud storage is authorized. So if you go to 1.iu, search cloud storage, make sure it's authorized there. Also, if you're trying to open files, they need to be on your OneDrive. So maybe this is creating like a 371 folder. And then any file that I put up on Canvas, you'll need to download it and then kind of drag it over into your OneDrive. So I'll kind of walk through this with the files we're going to use today. But those are kind of the two most common issues I'm seeing kind of with people being able to open up a file in Stata. If you're having any other issues, I'll walk through some other stuff today that might help. For some reason, I had some student, it won't let you drag and drop the files onto your OneDrive, but you can go to add file and like go through that whole process. So if you're not able to drag and drop it, try to manually go through the steps of adding it on there. I'm not sure what permission that is that it's not allowing you to do that. But just a kind of an additional step there to kind of get those files on your OneDrive. Okay. I also want to mention I will start this weekend using those in-class quizzes. Probably won't do one today, but Thursday might be a pretty strong chance that I have one of those to use one of those on Thursday. All right. So seeing not as many people as I would hope today. So hopefully, I can't stress enough. If you start falling behind in this class, it becomes very, very difficult to kind of recover, especially early on, try to get the easy points, easy stuff out of the way. After class Thursday, I will post the first kind of quiz and problem set. So it'll be everything that we've done kind of last Thursday and this week. It'll be kind of your first prior project with Stata. So I'll give you 2 weeks to do it. So you have a lot of time. It doesn't mean they'll wait to do it in a week and 5 days, because then we're going to be far removed from when we covered that, how you do that in class. And you're going to have a lot more questions. So start working on those early. I know it's your first time kind of using Stata to do something, so it might be, a lot more work on this first one, kind of initially getting going. So take a look at that once it's up there, get started early. The quiz, I'll get up some practice problems actually this afternoon. Start to think about the types of questions that I'll ask you on quizzes and exams related to kind of the material that we've done. First 2 weeks, really just review. But depending on how long you took 370 or the equivalent, might look. It might be kind of new to you this first 2 weeks, okay? I wrote things down to make sure if I don't forget anything, that should do it. Any other, oh, I know the other thing I was gonna mention. When we start working through these do files, I had someone come to me last class, or after last class, I'm not expecting you to re-type out all the do files as we go through it. I have it there so that it just kind of saves us class time, so I don't have to type out. I try to explain what the lines of code mean, right? But you don't have to like retype it all out. In fact, it's probably good to have that do file up when we're going through it in class. But I would almost use like the comments. I talked about using like the double backslash, how I have comments I added in. I would almost like take notes in the do file when I'm working on it, right? Things that I say in class, or maybe I add to the do file in class that weren't in the original do file. Those would be good things to kind of add in and make sure you're kept with. But by no means feel like you have to start with a brand new do file and type out every single thing that I'm showing you. Start with the do file that I posted and that I'm pulling open, and then kind of work from there, adding in additional comments and things that we go through in class. Is that any questions for me before we kind of dive into material here? Okay. All right. So I don't think we quite got there last class, but hopefully it should sound familiar. We're talking about things or variables being distributed. A lot of times we'll talk about them being normally distributed, right? We talked about, data can have skew left or to the right, but it can also be nice and symmetrical. This normal distribution is nice and symmetrical, and we see it pop up a lot, right? So I think I did go through at least to introduce and say, okay, we can have two variables that are both normally distributed, but their means are different, right? And so that's going to shift where that distribution is plotted. We also said that it can have different variances, right? And that's going to affect how kind of, we said, like squished or peaked that normal distribution is. So the special case that we're going to work with a lot today is what we call the standard normal distribution. So we talked a little bit about standardizing variables on Thursday. So just anyone remember, how do we standardize a variable? I would subtract. Didn't stay though. Yeah.
Subtract the mean, divide by the standard deviation.
Yep, we just subtracted by the mean, divided by the standard deviation. That gave us what we were calling last class a standardized value. Another word we have for these are going to be z values, right? It represents, once I standardize that variable, I've got a new variable, call it z, that tells me the number of standard deviations away that value was from the mean, okay? So the nice thing about this, here, this nice visual, right? I get this nice standard normal distribution. Well, it's always going to be centered around 0, right? Because the mean is always going to be 0 standard deviations away from the mean. And then what will end up also being true is that our variance always ends up being 1. But if our variance is 1, what's our standard deviation? Just the square root of the variance. So the square root of 1 is 1. So it has this kind of unique property in that the variance and the standard deviation are both the same and they're both a value of 1. Okay? So we can think about things like -2. If I standardize the variable or I turn it into what we call a z-score and I get -2, that's telling me it was that value is 2 standard deviations below whatever that mean variable's mean was. And then if I see, +1, it was 1 standard deviation above. Okay. So if I think about kind of a formal formula for these z-scores, I'm taking the value for x, whatever variable I'm interested in, subtract the mean, divide by the standard deviation. Okay. I already mentioned this. So, it's just the number tells you how many standard deviations away. If it's negative, that's telling you it's below the mean. Positive, it's telling you it was above. And then the mean will always have a z-score of 0. It's 0 standard deviations away from the mean. So we're going to use this today. And I kind of already walked through this. I didn't show you this slide, but we actually did it in Stata on Thursday. But, if I'm thinking about, if I'm subtracting the mean from this y variable, if I wanted to find the expected value of z, because I'm subtracting the mean from every single observation, the expected value ends up simply being expected value of y minus the mean. Well, the expected value of y is the mean of y. If I'm just choosing someone at random, right, kind of our expected value is going to be whatever that mean is. We're always going to have that these z-scores have a mean of 0. And then it just works out. We won't walk through the mathematical proof. But if we were to look at kind of that deviation of that z value from its mean, what we'll always see is that the variance is always going to be 1. So we have this mean 0, variance 1. We can then rely on a table, the z table, the standard normal tables that have been put together to do things like, oh, well, I jumped the gun a little bit. Before I kind of show you those tables, I did want to kind of bring this up because I think it's just kind of interesting. Why do we use this normal distribution and standardize it? Well, we see the normal distribution pop up a lot, especially with biostats, but in general, even productivity. We see a lot of things follow normal distribution. So here I had some survey data that was it followed people from the age of 16 and for 40 years. It's called the National Longitudinal Survey of the Youth. And I had this data set. I looked at the adults in a certain year and said, okay, well, let's look at a distribution of the height, right? I mean, this is pretty close to being symmetrical. I mean, it's a little bit off, but really close to a normal distribution, right? I'm not really big into CrossFit, but I saw them put some stuff out on a social media, and they were putting stuff out like this. And I was like, I don't think they realize how cool this is in the sense, well, I say cool, but this especially for the women, this is maybe I couldn't even draw a normal distribution, maybe a little more perfect than that, right? So human performance data, a lot of the times we see is also very close to a normal distribution. So it pops up a lot. It's not like we're using something that doesn't occur very often. Right? So why are we using z-scores? Why do we then go from this normal distribution to a standard normal distribution? I don't think I have it in my slides, but there is an actual function that you can map out what, there's a line on a graph. I could create a function that gives this to me if it's a normal distribution. And involved in it, there's pi and the mean and the variance of that variable. And we could integrate that function to say, okay, well, what's the probability if I chose someone at random that they are, 67 inches or shorter? But we don't want to do that integration every single time. A nice workaround is I can convert or I can standardize those original x values into z-scores or z values. Then I have this nice standard normal distribution where, because the standard normal distribution is always the same, I have to do the integration once. I can always go back. I don't have to do it ever again. Those numbers are just there for me. So that's essentially what we're gonna do, right? So maybe I want to know what's the probability that I see this X variable be between two values. It's normally distributed. I'm going to turn it into a standard normal distribution and then use our Z table. So for instance, let's say I had some variable in the value. I converted it to a Z-score and I get negative 1.29. Okay. Well, what the table does, well, I'll show you in a second, the standard normal table, if you look up a Z value, you can find the corresponding area to the left. Or said differently, the probability you saw something this many standard deviations away from the mean or anything even further, or anything below it. Right? So that table is always going to give us the area to the left. We might then have a little bit more work to do, and we'll kind of talk about some examples here in a second. But so the visual representation of the table is whatever Z value you look up, it's telling you this area to the left. Okay. Excuse me. So here's the actual table. So by looking at this table, right, it's going to have two sides. So the PDF is up there under the Files tab on Canvas. I didn't put any folders. It's just under the Files tab. You don't have to go anywhere to find it. It's got two pages, or if you print it out, it would have two sides, right? So one's going to be a bunch of negative Z values, and the other's going to be positive. Now, I'll walk through a couple examples where we only really need one side because it's symmetric. We can kind of use some tricky stuff. But let's say I was looking up that value of negative 1.29. So the first column is always going to be my first decimal, and then the the column headings are going to be my second decimal. So negative 1.2, I would go down here, right? Look at my first decimal, negative 1.2. Then negative 1.29, I go all the way over to that last column because it's got that second decimal as being, 9.09. Where those kind of two would meet, this is going to be the probability or the value that, or here's the probability that I see negative 1.29 or anything to the left of it. Okay. So I could also look up, 0. So notice if I look up 0.00, that probability is 0.5. Why? Because one of the features we also said about the standard normal distribution, really the normal distribution, the mean is the same as the median, and the median exactly splits our data in half. So here, the area to the left and the right of the mean should be 0.5. And then as I kind of start to move further away from that, notice what's happening to these probabilities, what's happening to this area. Well, as I move further and further to the left from 0, that area is going to be getting smaller and smaller and smaller. So you'll notice by the time I get to like negative 3.7, I'm out to the fourth decimal at this point. Like I'm getting really, really small probabilities. In fact, anything in the twos even, we're getting really, really low values here. Okay. Any questions on anything here before we keep moving? Like I said, should hopefully be reviewed, but just want to make sure we are going to use some of this stuff to do hypothesis testing, confidence intervals throughout the semester. So I want to make sure we kind of get a nice little review of it. The other half's just the positive values. So without going through this, the area to the left of negative 1.29 is 0.0985. So if I want to know what's the probability that I see positive 1.29 or anything lower, anything to the left, what value am I going to find from the table? Well, if I remember, this is a symmetric distribution. So the area to the left of negative 1.29 should be the same as the area to the right of positive 1.29. So I fold that on top of itself, it's symmetric, it matches up exactly. So if I know the area to the right of positive 1.29 is the same as the area to the left of negative 1.29, I know the area on the right was what, 0.0985, I think it was. So if I want the area to the left, well, if I'm choosing something at random, what's the probability I see something in between infinity and negative infinity? Or said differently, what's that area under my curve? For a standard normal distribution, it's always 1, right? It's every single possible value. Probably I see one of those values, 1. So if the area under the curve is 1, I know the area to the right of 1.29 is 0.0985. The area to the left has to be 1 minus that, right? So about what, 0.9 or 0.8? What, 8915? Remember the numbers correctly? No, 0.9, sorry, I said 0.8. 0.9015, right? So I can always, I don't have to necessarily rely on these tables, especially once I look up the value once. I can then sometimes use that information without having to really go back to the tables with this idea that I have a symmetric distribution. And you'll start to notice So visually, what is that looking like? Something like this. So right away, something that can kind of prevent you from making easy mistakes. If I were to draw out the standard normal distribution, so okay, what's the probability I see something that's less than 1.29? Well, automatically, I know this probability has to be greater than what? What's one value I can for sure say it's greater than? What's the area to the left of 0? 0.5. So the area to the left of this has to be greater than 0.5, right? So that can sometimes help me, like if I do need to like, do 1 minus or whatever, it can help me like put an initial bounds on what my final answer should be here. If I wanted the probability of seeing something below 1.29, I know that I should have a value that's positive, or it's positive. I should have a value that's greater than 0.5. It has to be positive, but greater than 0.5. And that's because that z value is positive, right? Anytime I have a positive z value, it's going to be over here, the probability has to be greater than 0.5, okay? Any questions on, that shouldn't be too bad. Go through this kind of quick. Stuff I think is a little bit easier. So we could look at different ones. So first of all, which of these should I hopefully be able to rule out right away? If I'm looking for a probability, what's the lowest a probability can be? -1. 0, right? Because if I'm talking probabilities, right, the very lowest, something just can't occur. Like there's no chance it can occur. That probability is 0. Okay? So we're kind of bound and we're looking at probability. If we go back to these tables, notice, even for the extremely small values, the lowest we could ever see for our probability is 0. Right? So there we go. So we can rule that one out. If I'm thinking about, okay, what's the probability it's greater than -2.53? So if I'm drawing this out, I've got -2.53, and I want the area to the right. What do I know that area has to be greater than? 0.5. The area to the right of 0 and the left of 0 is always 0.5. So if I'm going, starting at 0, the area to the right would be 0.5. I'm going all the way back to -2.53. I'm going to get something that's greater than 0.5. How much greater? Probably more than just 0.057 greater. So if I'm making an educated guess, I'm probably thinking the answer is D here. Now, if I try to use the table to look this up, what am I going to do? So I go to -2.53, I get 0.0057. Okay, that's my answer. Well, no, I wanted the probability that I saw -2.53 or greater. The table always tells me this is the probability to see this z value or anything below it. So I have one more step, which is I need to take 0.0057 and subtract it from 1. Okay. So if I do that, I take that 0.0057, I subtract it from 1. That should give me that 0.9943. And then kind of an easier one, if I just wanted the probability it's less than -. Well, then I just could grab it right from the table. I didn't have that additional step. Okay. Any questions? Yeah.
When you said that like the table always shows less than, is that for like all tables or just that specific thing?
That tables, I'm trying to think what table. We'll use the T tables a little. I can't remember how the F tables are set up. I think they might show you the area in the right. But for right now, we're just using these Z tables. That should always kind of give you the area to the left. Yeah, I think if you looked at different F distribution tables, some of them will report to you the area in the right tail because F distribution is used for things that you can only ever see positive values for. So you're only ever looking for the area in the right tail, but we'll deal with that issue. That's much later on in the semester. We'll start looking at that. So for now, yeah, the tables we'll be using gives us the areas in the left. You can probably find a Z table out there that doesn't. The one I posted is going to have, is thinking about the areas to the left there. Any other questions? Okay. I just put these up here. We'll see these values pop up a lot. You can kind of notice why. I mean, it's like 99.5, 99%, 97 point. These just tend to be some benchmarks that we're looking for. So we start to see certain Z values pop up a lot. Once we get to even linear regression and we're thinking about critical values, we'll see certain values pop up quite a bit. So I just got some more examples. I think seeing these work through or just thinking through this in different ways kind of helps. So if I've got some movie and they're going to make popcorn, right? Mr. Nanny too. So they think popcorn demand is following this nice normal distribution, mean of 50, that's the first number, we always have the mean. And the second thing that defines a normally distributed variable is its variance. So mean 50, variance 100, or a standard deviation of what? 10, square root of the variance is our standard deviation. So what's the probability that they make 60 pounds, they don't have enough? So the only way that they don't have enough is if demand actually is a value above 60. Right? So we're thinking about what's the probability that demand ends up being 60 or greater? Well, automatically, I know that probability has to be less than what? What's the area to the right of 50? So be careful, the area to the right, I think if someone said 50, it's a probability of 0.5, or there's like a 50% chance I see something to the right of 50 because 50 is my mean. So if I then want the area to the right of 60, I know that area has to be less than 0.5 or less than 50% if we're talking in percentages. The table's in terms of probability, so that's kind of what I'll say. We can go back and forth between those two. It's just moving the decimal. So automatically I know it has to be less than 0.5, so I know it's going to be not A, right? Now, if I'm thinking about, I can do this one pretty easy in my head. What's the Z value that 60 would become? If I subtract the mean, 60 minus 50 is 10. Divide by the standard deviation, which was 10. So 10 over 10, I'm one standard deviation above the mean, right? So I'm going to end up with a Z value of 1, right? We were kind of looking at some of these things before, like 1.29. The area to the left of that was about 0.1. So I'm guessing it's probably going to be C, but we can actually go through and figure this out, right? So I will draw this out a little bit though, just in case anything's in there. So kind of the visual to go along with what we're doing. I'm starting out with this quantity of popcorn demanded. It has a mean of 50. And we said its variance was 100, making its standard deviation just the square root of that 10. Really what we're doing is we're converting this value that we said, okay, what's the probability that demand is 60 or greater? So we want to standardize that value or turn it into a z-score. So what do? We take the value of 60 that we're looking at, subtract the mean, divide by our standard deviation. We get this z value of 1. Now, when we go to the table, we want the probability of seeing something 1 standard deviation above the mean or greater. The table is going to give us the area to the left of that value of 1. So we then need to subtract it. So I'll go back to here in a second. If I go to files and I open this up, download it so we can zoom in. Oops. There we go. So I'm going to go down here. Anytime I have an integer, it's going to be the decimals or zeros, right? So 1.00, so 0.8413. That's the area to the left. That's the area to the left of that z-score of 1. I wanted the area to the right. So I just need to subtract that from 1, and I get about 0.15, right? 0.1587. Okay. Any questions on anything I did there? Okay with that? Okay. All right. And these are like maybe some examples of like types of questions I could put into Canvas. Maybe we work through some of this z-value stuff, and I give you a question where you kind of have to apply it. I give you some time, you talk to the people around you, work with people around you. When I use these questions in class, it's more so meant for you to start applying and then realize what maybe the difficulties are of just seeing me work through a problem as opposed to then you having to put it into action, right? So this is an actual movie, right, with the cancer. It is hilariously bad. It's a Hogan movie, so if you want a good laugh, it's a great one. What if instead, so here, I don't even have to use the tables anymore now that I have this. This one should be an easy one for me to answer. So what's the probability the demand is going to be over 60 or under 40? So we already know the probability that it's going to be over 60. We just found that. So that was what? 0.1587. What's the probability that it's 40 or below? Well, what would the z-score for 40 be? If I subtract the mean, divide by the standard deviation.
The same.
Same, but negative, right? Because it's going to be 40 minus 50, so I get a z-value of -1. Well, the area to the left of -1, remember, it's a symmetric distribution, same as the area to the right of +1. So 0.1587 plus 0.1587 gives us that 0.3173 approximately. I think it doesn't quite work out because if you look at the table, there's rounding things with a fourth decimal, but yeah. Okay. Any questions on that one? I'm just trying to kind of give you different ways of thinking about using this standard normal distribution. Here's a nice screenshot from the movie. We can also, I'll do this for you on the dot cam as well. So just to kind of show you where it comes from. You guys are probably all smart enough that you can figure this out, but I like to be a little bit precise sometimes. So anytime I'm calculating a z-value, you can kind of think about these, any value I look up in that table is always, like if I look at 1.29, I'm always going to find that same probability over and over and over. So you can almost think about like every z-score has an associated probability, right? So I almost call it p-value, I almost jumped the gun, but it has an associated probability. So I could rearrange this, multiply both sides by that, add the mean to both sides. And now I can kind of work in what we call the inverse. Really, it's like, I think it's more like reverse, but we call this the inverse transformation because now I can start out with saying something like, okay, let's say that I wanted to know what was the cutoff for the 90th percent of popcorn demand that we were using before. Well, there I have the probability that I want. I want to know what value would give me that 90%, right? What would be the 90% cutoff there? Well, then I just plug in my mean, plug in my standard deviation, and I can get what? X is, what was the z-value associated with 0.9? It was approximately 1.29. So I get what? 62.9 would be the amount of demand that would have been my 90th percent cutoff. Okay. So I can work in the other direction as well. You can tell me a desired probability or kind of like cutoff percentile, and I can give you the corresponding cutoff value next. Yeah.
Re-explain how you explain that line and then how you got to 62.
Yeah, so here I knew I wanted the 90th percent cutoff, so I know that probability I wanted was 0.9. So what I would do with the table is say, okay, look, I know now the probability I want. I need to find the corresponding z-value. So I look here, I'm hunting around, looks like 0.9. I'm in between these two values. So I go over here, 1.28 and 1.29. So what I'll do in practice is anytime I'm in between two numbers, I always just kind of default choosing the higher of the two. Right? So anytime you're in between two on this table, use the higher of the two values. So 1.29, and then once I have that, that's where I'm plugging that 1.29 in as my z-value here. That gives me that desired probability of 0.9. So the 0.9 is never like being multiplied. I'm using that as a subscript to almost indicate I want the z-value associated with 0.9. Does that make more sense?
Yeah.
Okay. And then 10 times, am I doing math in my head correct? 10 times 12, or 1.29 would be 12.9, add that to 50. Yeah, yep. Any other questions? Yeah.
Can you explain again how did you got 1?
Yeah, so I said I wanted the kind of 90th percent cutoff, so I knew the probability I wanted was 0.9. So in this table, these are my probabilities. So I wouldn't look up 0.9 here because that's a z-value. I need to find how many standard deviations out I need to go to get, now I forget where, there it is, 0.9 as the desired kind of area to the left of that value. So how do I find that? Well, I go over 1.29 was the value that gave me 90%. Now that's the z-value I plug into my inverse transformation. Is that any other questions here? Just got another example. We would use the same 90% cutoff, so it's kind of nice. This is where I said that's the reason why I can kind of write that as the z-score associated with this probability, because it's always the same. Anytime I want to calculate a 90th percent cutoff value using this inverse transformation function, I'm always going to be using 1.29. So here, I can use this formula. I said it a little bit differently here, right? We can phrase things a little different. Not, I want the 90th percent cutoff, but what test score here would be in the cutoff to get in that top 10%, right? Well, the bottom 90, top 10, it's really saying the same thing, right? I'm looking for that cutoff value. It's going to give me that top 10%, or said differently, the bottom 90%, or the kind of the cutoff between the two. So if I've got my mean, I've got this exam score that average or the mean was a 72, the variance was 64. So take the square root of that to get my standard deviation of 8. Now it's just a matter of plugging and chugging, right? I've got my mean, I've got my standard deviation. We know that z value that should be that cutoff to give me 90% below and 10% above, we just looked it up, was 1.29. So it's just a matter of, right, getting those values now plugged in and then figuring out what that score is. So here, what is it? There we go, 82.34. So hopefully it's not the case for the exams in this class, but hopefully I have a little bit higher of a mean there. But you could, like, if you ever have classes and I think that they can release, I know you can see the mean on Canvas if the instructor allows it. Sometimes I think you can see the standard deviation or variance, but you could do this for yourself. You could like figure out like what was the 90th, like what would have put me in the top 10% of the class by using this inverse transformation function. Like I said, I know there's a setting you can see like the mean of different assignments that you post on Canvas. I don't know if all instructors use them. I probably will because it's stats and it's kind of interesting to think about things that way. I think you can do standard deviations as well. If not, I can do this behind the scenes because I have those values. Right? Any other questions kind of on this before we keep moving here a little bit? Okay with this? Where are we at? So I jumped the. We don't need to talk about that yet. So I think we're gonna diverge a little bit and go to Stata. So just as a kind of reminder, we've got the program itself where all the code is executed. Nothing here is saved, right? You can save the data sets, but none of the output gets saved, right? So what we do is we try to save the code in these do files so that we can always go run it later and get the exact same output snippet. So I think here you can do it from either the program or you can open the do file editor. I just am doing it from here. So I'm going to go to open, go to my OneDrive, wherever you've got your created folder, you should kind of drag and drop the files in there. So I'll actually show you what this looks like. So let's say, that's all on the home page. It's probably easier to do. So right now, we're going to be looking at this review of statistics, kind of picking up where we left off. However, we're going to be using this election data, right? So what you would do, kind of download this election data. Okay. Go back to files. I'm also then going to, where is it? I know it's in week 2. Download this review of statistics file. Now, for some of you, you'll have to go to kind of this Microsoft 365. You can search for that on one.iu. And then you'll have to drag and drop your files here. Or some computers, like I said, I was having some people had some issues. They actually had to go to, where is it down here? Go. So this one's set up, I can't show you because this one's set up that you can drag and drop. If it's not allowing you to drag and drop, there should be an option. Here it is. Create. No, where is it at now? This interface is different than the one I've ever shown me. You should be able to, there should be like a thing up here where it says like add files, and you just have to go through like search the actual folders and then add it manually that way instead of dragging and dropping. This one, it's kind of set up within this computer, you can drag and drop. So I would just go to downloads. So now I've got these downloaded and drag them over here, drop them into whatever folder I want. I think another way that sometimes you can see it displayed is if you're like on a university. So sometimes under this PC, like if you're on a university computer, your OneDrive will pop up down here. You can click on it here and then drag and drop files, copy them that way. Like I said, I don't have an interface to show you right now, but occasionally, if it won't allow you to drag and drop, then there should be a little like thing in the top left that says like add, and then you'll go to add files, and you just have to upload the file manually that way. So you'll download it from Canvas, get it onto your OneDrive, and then you can get rid of all of this, maybe. I can actually open up from my OneDrive. Here I've got, I won't use that one because I know I have a different one here. Got it floating in week 2 materials. I've actually got both of these in here. I don't think we're going to get to this one today, but just in case we do, I already have it pulled open. So I'm actually going to open up, I selected both of these. I'm going to open up both Jew files here. And this is, I like that it's big, but this is a little bit much. So let's just zoom out just a smidge. Okay. So this has kind of all of my code that once again, you should be able to download that do file from Canvas, open it up, follow along with me, add your comments as we kind of work through it. So we did a lot of this last class. I'm going to come down to here. So we had the standardized variable. We're going to start out where it says kind of week 2 code, right? So I'm going to open up a different file than we were using last class. So it's not this state cigarette tax data. It's going to be this election data. Right? Now, I think I accidentally didn't save my global that I showed you. Or yeah, actually I do have it up here. But just for the sake of showing you, even if you don't want to use these global pathways, you're always on the same computer, so you don't really care. You can always go to File, Import. Now, last class I was kind of showing you a CSV file. Let's instead do an Excel spreadsheet. Right? I think some of you were having problems where, for whatever, the CSV wouldn't even download as a CSV on your specific device. It was downloading as an Excel file. You can always download or import an Excel file as well. There's kind of 2 different caveats though. So I'm going to go to Browse. I'm already kind of in my OneDrive, but you would go to your OneDrive, find the file that you want. There it is, election data. Hit open. Now there's 2 things we're using Excel file. The first is, more often than not, the first row in our Excel file is the variable names. So we want to make sure that we're not treating that like a separate data point, that the first row is our variable names. Okay. Excuse me. The second kind of point I want to make for this is, if you have some familiarity with Excel, the file of Excel is called a workbook. Within a workbook, you can have multiple worksheets, right? So here, I actually had the raw data. There was some like missing values. So I didn't want to deal with those issues yet. So I created another one where it has non-missing values. So we're going to select the worksheet that we want to import. We can't import all of the sheets at once. We have to only do one at a time. So we just want to use this worksheet, which is non-missing. Okay. I'm then going to hit OK. It runs this line of code. And then, in practice, what I would want to do is copy. I've already got it here with using a global, but I would kind of paste it if you were doing this on your own. That way you can always come back and kind of start from the very beginning, right? If you make some errors or mistakes later on, you can always go back up and redo this. But this isn't getting saved, right? Just by running the code, it doesn't get saved there.
What did you do with like the non-missing thing?
Yeah, so when we were under import, right? I first selected to make sure that the first row was variable names. This worksheet option, there was multiple worksheets in that file. So if you open up the actual Excel file, there's 2 different tabs. We want to upload that tab that it's called non-missing. So that's just the name, right? That's not like an actual code. That's just the name of the actual tab in Excel. And then I just hit OK. So now I've got all this data. Okay. Any questions up to this? So we can upload different types of file or import different types of files. Well, I'll show you this a little bit later on. We run a little bit more code. I'll talk about saving files, like the actual data file. We want to try to avoid that initially. I'll show you an example of maybe where it makes sense, but you don't generally want to save the data itself because you'll lose the original data. Like you don't ever want to write over the original data. So if we open this up and it was already in a state of format, it wasn't Excel, when I save it, it's going to rewrite over the old one, I lose the initial data. So we'll talk about ways to avoid that here in a second as we work through this do file. So I've got it opened. For whatever reason, I don't know why I had this type in here twice, but maybe it was because I wanted to show you that what can happen. So we talked a little bit last week about there's this rename command. I'm just going to rename some of the variables so they're not as long, right? So I had all this county level data, and I believe the variables are the proportion. Yeah, so it says percentage. This is why I wanted to rename them. These aren't percents. These are the proportion of the county that ended up voting for Trump and Biden. So wherever I got this original data, it's kind of, they shouldn't have named it that way, right? So I'm going to rename that variable, which is percentage 20 Donald Trump. And I can, widen this out to see what the exact name is. Or I can also, and this is a little bit squished on, let me see. It's a little bit squished, but here's all my variables. Oh yeah, I can see like what the total name are. I can copy paste from here what the actual name is. But I've already got it typed out for us, okay? So I'm just going to rename this to Trump 2020, and it's the proportion of people in that county who voted for Trump in 2020. So I'm going to run that code. Okay, I can see now when I go to the data, okay, it renamed my variable, right? Now, in order to see the full name, I don't need this to be near as wide, okay? Now, if I go back to my do file, if I tried to run that same code again, once I rename the variable, this variable no longer exists. So if I tried to run it again, it's going to give me this error because it can't find the variable. I already renamed it. So this is why you want to save your code. You don't need to kind of re-enter it every single time. You also, once you rename a variable, you overwrite something, that no longer exists. It's the new variable name. That might be obvious, but I try to think of things that I don't know, might kind of come up. So if I don't want to delete this and I just want to quickly have it not do anything, I can always just make it a comment. So ignore this basically. I'm also going to rename this other variable, which is the Biden variable. So it kind of now gives me this nice, here's the proportion of people who voted for Trump in 2020 in that county. Here's the proportion of people who voted for Biden in that county. Okay. Yeah.
I think the data which I have is of when Hillary Clinton election somehow and not the Trump and Biden one.
So are there variables in here? I upload the wrong one or is it the wrong one? Well, I know we can test. Let me see. Didn't have anybody from my previous sections. So let's say I just copied this one off of the import. Import Excel. You all right? I put up the wrong election file. Thank you for saying something. This is yep, 2016. Let's try rewriting this thing. Now I'll give it a second to catch up on this. Oh, this is the I don't know how that got mixed up. That's what I'm downloading. This is the one I just put up there. So let's make sure this is right now. This is the 16. Why is this? So this is 2020. Oh, it is the right file. Gosh, bless it. What was I doing? I'm an idiot. I was looking at the wrong tab. You're trying to open up the raw data tab. The one I was using was the non-missing tab that we went through. So it's the right file. You just had when you went to import. I was like, surely I didn't do that. I didn't do that. So if you go to open this up. So yeah, this one is the 16, but if you change it to the correct tab, this is the one that had the 2020 data.
Okay.
Yeah.
Thank you. Sorry about that.
Sorry. Well, I confused myself, so don't apologize to me. So then we can rename those variables, right? So another quick thing we can do, and there is a way to do it on the interface. There's an option you can go to, I think it's like through statistics, and you can find it somewhere. It's create a quick histogram that gives you a quick snapshot of what the distribution of a variable looks like. So we're going to use this unemployment rate variable here in a second. I just want to get an idea about what it looks like. So I'm going to use that hist command that says create a histogram where you look at all the values for unemployment and you kind of put them in bins, create this histogram that kind of gives me a quick, dirty look at the distribution of the data. So I've got the unemployment rate variable. Another thing someone last section was telling me, like, I kind of couldn't get this thing to run. I probably have failed to mention this. Stata is, and there's a reason why, hopefully you see I am capitalizing, it's case sensitive. So if I tried to run this code and I just type in unemployment, there's a variable. It looks like that doesn't exist, but that's because if I hunt through all my variables, I'll see that it's actually capitalized. Well, it can run that code, and it's taking a second, but it's going to create a histogram for me. So it is case sensitive. So make sure when you're naming variables or renaming, probably good practice. Like I don't do this, so I'm kind of being a hypocrite, but it's probably best practice to just always keep everything in lowercase. I just, for me personally, like I don't type that way. So like I always do the reverse then. If I try to always do lowercase, I then start to try to capitalize things that shouldn't be. So it's kind of individual specific, but it is case sensitive. So here's my unemployment rate variable. You can kind of see it's kind of normally distributed, but you know, there are some counties with really high unemployment. So we kind of have this longer right tail. So we would have this kind of positive skew to our data, or right skew data set, which means what is probably true about our mean relative to our median. If I have right skew data, these extremely high unemployment rates, and these are in percentages, so like 20%, 10%, are going to pull my mean to the right. So yeah, my mean is going to be a lot higher than my median because it still only counts as one observation. So we could even prove this to ourselves. We use this last class, that sum command that just summarizes that variable pretty quickly. So if I hit to run this code, oh, there we are. Oh, and I forgot. It doesn't give me the median unless I add in that detail option. Now, if I look up here, my mean is 6.3. The median, which is that 50% cutoff, is 6. So sure enough, my mean is greater than or to the right of my median here. Okay. So, but we can get, usually we can kind of see that from this, like, if it has some skew to it, we wouldn't really have to use that summarize command, and we would kind of know, oh yeah, these extremely high values are going to pull that mean to the right and not impact the median as much. Okay. Any questions in this before we keep? Same kind of thing, this doesn't get saved. So if I ask you to do a histogram, you can take a screenshot, you can actually save it as a picture. But this is, once you close out of the program, this goes away. Okay. So we're going to go back here. Actually, I don't need this anymore, so we'll get rid of it. I talked last class, we can kind of do this thing where we use the some built-in programs or packages that we can't like really see that exist behind the scenes. So anytime I put instead of gen, I put egen, that tells Stata I want to generate a variable, but I'm pulling it from, I don't know why it's E, but that just tells us I'm pulling it from this package E that has all these saved functions in it. One of the saved functions is calculating a mean. One of them we looked at last class was standard deviation FD. Right? And then you can do the median, you can do all the different types of statistics. So here, we're just going to create this new variable, call it unemped mean, and it's going to be the mean of our unemployment rate variable. So this is something we kind of looked at last class, so we'll kind of go through a little quicker. I've now got, anytime I create variables, it puts it at the very end of my data set. So it created this unemployment mean. It's the same value for every observation, right? It was just calculating one value. I also have the unemployment rate variable here. So what I could then do is say, I think that maybe, depending on the economic conditions in that county, because it was currently a sitting Republican candidate, maybe things weren't good in their county, they're more likely to vote for Biden, the other side, right? This is also a point where I didn't give this spiel, I think, on day one, and I probably should have. I gave it to my intro micro classes, but I think they call it intellectual diversity or something. We might touch on some political issues. I don't like any of the candidates. I hate all of them. Well, actually, I didn't mind RFK, and now he kind of jumped ship and kind of pissed at him. So, but I generally I'm very nonpartisan. I like to look at issues and we can think about them using our economic skills, but I'm not making any statements about what's right or wrong or what political party is correct. Here it just happens to be, I thought it was kind of interesting. The election's coming up. Could work with some old election data. If nothing else, start to try to make models that we can maybe even predict the outcome of, you can bet on that. So, there's maybe some money to be to be made if you can get a good accurate model and make some predictions here. So just because we're looking at somewhat political things, I'm by no means going to be on either side, right? So here we're just trying to understand why are they voting the way they are, or at least what are some patterns. So I had this thought, so I was like, okay, I want to create this new variable. And I want to put it a 1 to identify if the county had above average unemployment, and then 0 if not. So these variables that we'll create that are 1, 0 are I quite often refer to them as indicator variables. You might see them called dummy variables, different texts. So we're going to create these dummy variables that we kind of identify different groups, right? So how am I going to do that? I'm going to go back to my do file. And I'm going to generate or create a new variable, and I'm going to call it high unemployment or high unem. So anytime I have a conditional statement, like I want to check to see if this is true, is the unemployment variable value for that observation greater than this unemployment mean that I calculated? If that statement is true, once I put those parentheses around that condition, so notice here I put parentheses around this conditional statement. If that statement is true, it is going to put a 1 in for this variable that I'm creating high on it. If it's not true, it's going to put in a 0. So I'll run this, and I have these stacked side by side so we can kind of easily see anytime the unemployment was below the mean, 0. Anytime it's barely above, but anytime it's above the mean, we get a 1 in there for that variable. So we would call this like a dummy or an indicator variable that I just created. Okay. What I then might be interested in is, okay, what is like the breakdown, right? I think it might be 50-50, but I know there was some skew to this data. So it's not going to be that 50% of my counties are above the mean and 50 are below. I can do this in 2 ways, right? So the first, I can kind of use this tab command, right? If I use tab and then this new variable I created, what it's going to do is count up the number of observations for every possible value for that variable. Well, an indicator variable, there's only 2 values, 0 and 1. So it's kind of nice and easy to look at. Okay, I've got about 55% of the counties are below the mean, and about 45% are above. And that was a result of that skew that existed. Okay, it wasn't a 50-50 split. And I can actually also have the number of counties if I was interested in that. Right? How many counties are there in the data set? Now, notice here, I can kind of get an idea. Okay, there's about what, 45% of the counties are considered high unemployment. There's another way I can get at this. And if I just use this summarize command, think about what the mean of this high unemployment rate variable would be. So the mean, I would be adding up every single observation's value for this variable. Well, they're only ones and zeros. Anytime I add a zero, what happens to the numerator of my mean? Nothing. Adding zeros and change. So that numerator is only going to be counting the number of counties that are a 1 for that variable, which are only the counties that had above average unemployment. So I'm going to have in my numerator all the counties that had above average unemployment, divide by the total number of observations or the total number of counties. So it's going to give me not the percent of counties with high unemployment, but the proportion. So anytime you take a mean of a 1-0 variable, it's still a mean, but we often call it in statistics, it represents a proportion, right? So it's going to be somewhere between 0 and 1. So it should be, what, 0.4488, unless I'm lying to you. Sure enough, if I use that sum command and get the mean of this 1-0 variable, it tells me the mean tells me the proportion of the counties that had a 1, or in this case, had high unemployment. Okay. Any questions on that before we keep moving here? 20 minutes. All right, so you could do the same thing with low unemployment. So you can, do greater than, less than. It's really the same thing. I'm not going to use this for anything. I think I did want to show you this though, and that's why I grouped it together. If you had these typed out, you can run multiple lines of code at the same time. I usually in class do it one by one to not like overload us. As a semester goes on, we might run a couple more lines if we're already really familiar with it. But I can run multiple lines of code all at once. This proves to be the same thing. I could do low unemployment. The percent of counties that have low unemployment is 55.12. If I take the mean of that low unemployment rate variable, sure enough, I get kind of, it looks a little bit different, but it's because it's just rounded to a different decimal, right? 0.55. I just get the proportion as opposed to the percentage. Okay. So on that first assignment, if I ask you for the percentage or, for the proportion, you could use either method. You only have to use one of them. But then you would have to report that number because I can't see that. All you're going to submit is your do file. You can't, there's nothing to save here, so you can't. So you would maybe put in as a comment, here's the line of code, sum low on M, and then below it put a comment 0.5511 or something like that, right? Kind of depending on the type of question. So I think it's probably easier to do it that way. Some people like to just have all their code in a do file and then type anything that they would have had to put as a comment, put it in Word and upload 2 documents. I don't care either way. Both are fine. I find it easier to kind of do it all in the do file and just use the comment system, but everyone's different. Okay. Any other questions before we keep moving on this one? Shouldn't be too bad yet. Okay, so this gets a little bit different. Let's see. Got our high unemployment. We'll ignore this for a second. I think I have this out of order, so I'm gonna cut. Oh, thank you. Nope. I'm going to cut and paste this so that's grouped a little bit better. So I have now this low unemployment rate variable created. Okay. So I was running those lines of code. I also had that variable, which was the proportion of people in that county who voted for Trump in 2020. So I had this thought, maybe low unemployment, high unemployment rate counties voted a little bit differently. So I can use this by sort command. And what this does is it chooses whatever variable I tell it. So here's the low unemployment rate variable. It's going to sort the data based off of the values for that variable. Well, the reason why this is kind of handy with one of these indicator variables is there's only 2 groups. All the counties that have a 0 for low unemployment and all the counties that have 1. So it's going to sort them, and then by those 2 groups, by those 2 different values, it's going to summarize this variable, which was the proportion of people that voted. So it's going to give me the average kind of proportion of people who voted for Trump in low unemployment counties. And it's also going to give me the average or the mean for those who voted for Trump in who have a 0. So it would be not low unemployment, but high unemployment. So if I run this code where I use the by sort and kind of the syntax here, I've got to use colon here. So then we'll get this. It spits out at me, so it runs the code. It then says, okay, for the low unemployment value of 0, so these are going to be counties that don't have low unemployment rate, right? They were actually not below the average. 63% or proportion of 0.63 voted for Trump, whereas all the counties considered to be low unemployment, a much higher percent of them ended up voting for Trump. And that kind of makes sense, right? Like they had low unemployment and he was currently the sitting president, they might think, yeah, why would I want him to be whereas the other counties might not, right? So we can kind of start to break things down like this and look for differences between groups. Okay? Now, at this point, I want to make a point, which is this tab, the reason why I typically use sum instead of tab, it works great for indicator dummy variables. But if I use it for a continuous variable like unemployment, and it's not even truly continuous, it tells me the number of observations for every single possible value. I mean, okay, I guess this is interesting, but it's also a lot to look at. It's not really as useful to use that tab command when you have continuous variables. But when you just have like these indicator dummy variables, it's enough fine way to kind of get at, kind of how many you have in each group. But I just wanted to make that point. If you start, and in fact, if you do this for large data sets with truly continuous variables, that tab command will like sometimes freeze the program. So try not to use it when you have continuous variables. So I'll get rid of that because we don't want that. Okay. So I don't just have to summarize. The problem with summarizing is, right, I told you everything that's here just goes away as soon as I close the program. So if I want to actually save what the proportion was in low versus the non-low unemployment rate counties, one way I can do that is still to use this by sort command. But now I'm going to use the ECON package. I'm going to use one of these built-in functions, which is I want to calculate what these group means are. So what is the mean of the proportion of people who voted for Trump in 2020 in these two groups? What are the two groups? Well, the only two values for this low unemployment was it a 1, the group that had low unemployment, or was it in the group that had not low unemployment? So it'll calculate the means for both of these groups and then store it as a separate variable. So by this variable, the two different values for it, use the ECON package where I can use the mean function, create this new variable, which is the mean of the proportion of people who voted for Trump in those counties, but it separates it up into two groups. So if I run this code, everything goes. Now, if I look up here, well, first of all, it's sorted everything. So it's by sort, BYS, by sort. So it's sorted all the data, and then by all of the values that are 0, it's created, well, the average or the mean proportion of people who voted for Trump in those non-low unemployment rate counties was 0.63. I got to scroll all the way down. Here, once I get to where there's 1s, these are all low unemployment rate counties, right? The proportion of people who voted for Trump in those counties was a little bit higher, closer to what, 0.68 even, 0.67, 0.68, okay? So I can store, and now if I wanted to save this, this is where, if I go to my program, let's say I didn't import an Excel file and I opened up an actual stata.dta file. Well, if I save it, like if I just go up here and I click the save button, it would write over the old file. And let's say I did something where I dropped some of the variables, those are gone now. I'd have to somehow go back and get the original data. If someone gave it to me, now I got to go bother somebody. So what's probably better practice is if you want to save changes you've made, which if I later on in the semester, I'll give you a .dta file. You're probably going to want to save your own maybe along the way because you might not sit down and do it all at once, right? You might do it in one day and then work on it the next day. I would just go to your folder on your OneDrive, wherever it is, and do, maybe you want it to be called the exact same thing, but on the end, I would add like your initials or my edits or something kind of indicating like this is the data file I'm saving. I don't want to rewrite over the old file. So now if I go ahead and save this, and go to my OneDrive, where did I save it? No, I don't know if I said this right. Oh. Maybe it was just working on it the whole time. I did write to ECON. There it is. It was just taking time. It just took time for it to save, right? So then I can have this separate file. I can just go back wherever I left off, open it up from there. It's just better practice to do that because you don't want to lose that original data set. Okay. So like I said, use your initials, my edits onto the end of it. Might be a good way to do that. See, it's kind of a DTA or a stata file now. Okay. All right, let's go back here. Any other questions for the game? Okay. I did a similar thing just to kind of show you some additional stuff you can do. I won't waste too much time. We could do the exact same thing, but high proportion white counties. So there was some variables in the data set that indicated the percent of the county belonging to different racial or demographic groups. So I don't know. I think it's maybe interesting. Like create this variable, just a 1 if they had more than 80% of their county's population white, 0 if it was anything below it, 80 or below. I then summarized it. I don't necessarily need to look at the summarization yet. I want to just kind of keep moving because what I do want to kind of show is, okay, is there going to be any difference in the proportion of people or proportion of counties that vote for Trump by this new indicator variable? Sure enough, when the portion of the county is extremely high percentage white, there's a much higher proportion than when it was below that, right? So I then want to combine that with, okay, what about really rich neighborhoods, right? So I create this new income high. Well, we're really wealthy counties more likely to vote for Trump or vice versa. So I'll create that, right? What I can also do, I'm going to get this all in one line so it makes a little more sense. I've up to this point only used one conditional statement to create these dummy variables. I can also use more than one. So here I'm going to create this new variable, which is either it has high income or it has a high proportion white. So I'm now using 2 conditional statements. Is the county, does it have a 1 for this high proportion white variable that I created? Or this vertical line represents or is the income high? And here I don't say is it equal to 1, I say is it not equal to 1, right? So anytime you want to do not equal to in stata, it's an exclamation point and then an equal sign. So what this is going to do, I'm using 2 conditional statements. I could have done not just an and, not just an or. I could have done an and, in which case that's just the and sign, right? But if I want to do this or, this is going to kind of pick up all the counties, at least this is where my mind was going, that have a high percent of their population white, or they're kind of like a poor community, right? So I'm really picking up a lot of these like rural Indiana counties probably, right? So I've now got this new variable that I can create based off of 2 conditional statements. I then kind of look at the summary of that. It's even more pronounced where if I was either so remember this was like not being a high income. So if I was a not high income county and I had a high proportion of my county be white, the proportion of those counties voting for Trump was 0.66. Well, as if reverse, if I didn't belong to that group, so this was more like high income counties that had maybe not as really high white percent populations, the proportion that voted for Trump was only about 0.43. Pretty stark difference there, right? And you can play around with all the different variables, do different combinations, and kind of try to understand, if I'm thinking about, if I'm a campaign manager, where do I, economically, where are my resources being optimal? What's the optimal allocation of my man hours or volunteer hours? Like, what counties are we more likely to be able to kind of get more votes out of? Now, there's better ways of doing this, like with regression, but at least this is like kind of a quick way of thinking about it that way. Okay. So I know there's a lot of econ majors, but like, I mean, to me, like even being like an econ major, you can find yourself working in like a campaign manager or something, because like if you have these skills and tools, like at the end of the day, like it's how do I allocate these scarce resources of like volunteers and actual dollars to like maximize our output of winning as many votes as possible. Or I get that it gets a little bit goofy with the electoral college system, but right, winning as many electoral votes in that instance as possible. Okay. Any questions for anything I did here? I've got one thing I just want to kind of set us up for next class that we'll kind of go through in the next 5 minutes or so. Lead me up to this point. Okay. So we left off So we've been talking about distributions, the standard normal distribution. More often than not, we've kind of assumed when we're talking about all that we have population data, right? I was using all the Greek letter notation because we're looking at population statistics. In practice, I probably only have sample data, right? I might be interested in some habit of or average GPA of every IU student, but I only have like a set of 50, right? I only have a small subset. I have a sample, right? So the way that we're going to talk about these samples is we're going to use lowercase English lettering. So instead of capital N being like our total number of observations in our population data, lowercase n, total number of observations in our sample data set. Each observation is just going to be indicated by subscripts. So the very first observation's value for this variable y subscript 1. The second person or company, country, whatever we're sampling, second observation, the value it takes on for y subscript 2, so on and so forth. Okay? So what we're going to be assuming about our observations is that they're essentially what we call IID, or independent and identically distributed, right? So selecting you as the first person in my random, if the second person I chose was, oh, well, your friend, you can just give me your friend's name. Well, that's not independent because your friends for a reason, they probably have characteristics that are more similar to yours. Now I'm not getting a completely random person, right? So we want to make sure that we're basically all that means is we're completely randomly selecting people into our sample. Is what we want to make sure of. And we'll talk about some issues if we don't, what can arise. So when we're talking about a sample mean, it's the same exact process of population mean. We just add up all the possible values for this y variable and then divide by, now it's not our total population size, but our total sample size. So really it's the same thing, just the notation changes a little bit. The procedure is exactly the same. We will now indicate not with the Greek lettering mu, but whatever our variable is, kind of with a bar. So y bar, where a random variable is y, our sample mean y bar. Okay. So regardless of our sample size, it doesn't matter if I have 50 students, 100 students, 200 students in my sample data. What'll end up being true is, let's say I went out and I got 50 random students, calculated their average GPA, wrote that number down. Got another 50 random students, calculated their average GPA, wrote that number down. I continue to do that. I do like 1,000 different times, get 1,000 different samples. If I were then to take those 1,000 different samples that I have written down, and maybe I have them state, I do the hist command, they will always be normally distributed, well, with one exception we'll talk about next class, but they'll always be distributed around whatever the true population mean is. Okay? So I'll prove this to you next class with some actual data. There's a mathematical proof, but I think it also is kind of intuitive. If I'm taking enough samples, sometimes I'm going to get a sample mean that's a little bit below what the population is. Sometimes I'll get one that's above. Sometimes I'll get one that's right on. And the likelihood of seeing those different values will follow kind of the likelihood that exists with the original student level data, right? Before I was kind of grouping them together and calculating these sample means. So we kind of say if that expected value of our sample mean is the population mean, and we need a certain sample size, which we'll talk about next class, for that to be true, we'll call it unbiased. We say that it's consistent. Did I have another bullet point, hopefully? Yes. We say it's consistent if we have over a certain sample size, if the variance on our sample means it's the original variance of the data over our sample size. So why does this happen? If I'm just choosing people at random, I could get a GPA value of 0.2. Hopefully not a lot, but I could get a really low value. I could get 4.0. If I take 50 random students, what's the likelihood I'm going to see 0.2 or 4.0 as the average GPA across all 50? Not very likely, right? So the higher the sample sizes I take, the more likely I'm going to be seeing sample means that are kind of in the middle, right? Right around that true population mean. So as I take higher and higher sample sizes, our variance of our sample means is actually going to go down, right? When the denominator gets larger, this fraction gets smaller. So as I take larger samples, I'm seeing sample means that vary less and less. I'm actually pinpointing down just based off my samples where that true population mean is. That's a good thing. We're the first time of many that I mentioned, having higher sample sizes is almost always a better thing, right? Oh, I say better. That's kind of not a very good term. It allows us to pinpoint down where the actual population values are a little bit more accurate. Okay. All right. I think that's good for me. We will run through some simulations with some actual data, and I'll graph graph these out in data and show you that these sample means are normally distributed around the true population mean, and the variance will be the original variance of the data over the sample size. If you have any questions for me, I'm try to answer them after class. Otherwise, I'll see you guys on Thursday.